As we delve into this world of chemistry, we need to spend a little bit of time talking about the findings behind the development we have today. How do we know how an atom's constructed? How do we know how molecules come together? All of that kind of stuff. And so this all falls under this purview of historical atomic theory. First person we're going to talk about is Democritus, 4, 460 to 370 BC. He was the first person to realize that everything was composed of atoms. So he was the first one to hypothesize that everything around us was composed of an atom. He also realized, though, that not only was everything composed of an atom, he's the one who realized that atoms are indestructible. They're indivisible. Now, we know that's not 100% true. We can break down an atom into its subatomic particles, protons, neutrons, electrons, but it no longer behaves as an atom. So he was the first one to really come about this idea of that everything is composed of an atom around us, and the atom itself cannot be broken down further and still behave how it should behave. No, if we break it down further, it no longer acts as an atom. Next up, we have Robert Boyle, and we will revisit throughout some of our studies, like we have Boyle's law and our gas laws, stuff like that. But Boyle was the first one that really started looking at experimentation. He wrote the book The Skeptical Chemist in 1661, and so he did a lot of quantitative experiments. He decided that experimentation was the definition. He was the first one to develop the experimental definition of an element, but he also helped just emphasize the importance of experimentation and empirical observation. So before this point, a lot of it was very theoretical. A lot of it was very just, this is what we believe is happening. He's the first one that really started pushing we need to test it. We need to actually experiment with it and prove what's happening. So he's kind of the forefather of breaking apart and making experimental chemistry or experimental science really a thing and really helping prove what we know today. Next up, we have Antoine Lavoisier. He was the first one to realize that mass is conserved in a chemical reaction. So what this means is that the total mass of the reactants equals the total mass of the products. Even with he did this through combustion reactions. So a combustion reaction is where you burn something, okay? You burn something in the presence of oxygen and you produce CO2 and water. You can produce other things as well, depending on what else is in your sample, of course. But if you just have carbon, hydrogen, oxygen present, you produce CO2 and water. And so he realized that when he burned something, the mass that went in equaled the mass that came out. Even though the reactants and products were different compounds, we had this idea of conservation of mass. And that the law of conservation of mass is one of the really important ones that kind of stays in the not so distant background of our knowledge throughout all of chemistry. Next up, we have John Proust. He was the one who developed the law of definite proportions. And so he realized that substances have the same chemical makeup regardless of how that substance was prepared. Doesn't matter how it was made, the substance itself will have the same chemical makeup. We'll spend a little bit more time on law of definite proportions, law of multiple proportions in just a couple slides. Next up, we have John Dalton. He was the founder of the law of multiple proportions. So he realized that all atoms in a given element are identical. Atoms of different elements would vary in mass and size. Multiple proportions was this idea that reactants will always combine in a set of whole number ratios. And so the law of definite proportions is things like NaCl. Again, I'll show examples of this in just a sec with NaCl as the example. No matter what mass of NaCl I have, it always has the same ratio of sodium to chloride. Law of multiple proportions will look at CO, carbon monoxide, and CO2, carbon dioxide, and see that even though it has differing numbers of elements combining to itself, they're doing in whole number ratios. We also have the atom itself and a lot of theories and models that went into the atom. So first up, we had this idea of a solid sphere model, and that was developed by John Dalton. So you can see here, you can read these yourselves, but the idea of we've got this idea of the atom. He recognized that atoms, a particular element, differed from other elements, but this model did not account for the fact that atoms are actually divisible. He felt that atoms were indivisible, but they actually are. They're comprised of subatomic particles, protons, neutrons, and electrons. Next up, we had the plum pudding model from J.J. Thomson. And this model was popular for a little bit of time, um, still taught kind of frequently, the plum pudding model, and it recognized that electrons were in the atoms. He realized the electrons were in the atoms. And again, you can read through here and see how. But the problem with Thomas's model was that there was no nucleus. It didn't explain later experimental observations. Next up, we have Rutherford's model, which was the nuclear model. He realized there was positive charge that was localized in the nucleus of the atom, but it didn't explain why the electrons remain in an orbit around the nucleus. Why is that happening? Niels Bohr comes along and develops the planetary model. So it proposed the stable electron orbits and explained the emission spectra we see of some elements. We will talk about emission spectra later in the semester, but emission spectra is like the cool, colorful lights outside of stores and stuff that you plug in. You see the bright lights. That's like an emission spectra. We take gas particles, we heat them up, and when they emit back down to their lower energy levels, they emit at a specific color wavelength. The problem with Bohr model was that um, moving the electrons should emit energy and collapse into the nucleus. The model didn't work well for heavier atoms. Then we have the quantum model from Schrödinger. So it shows electrons don't move around the nucleus in orbits, but in clouds where their position is uncertain. And this is the most recent model, but it's still widely accepted as an accurate model of the system. So we use the Bohr model often to explain because electrons do have set energy levels they're allowed within, but the Schrödinger model is actually more correct than the Bohr model because although electrons have specific energy levels, there is like electron cloud that the electrons are moving in. Okay, so let's talk a little bit about the two laws I said, law of definite proportions and law of multiple proportions. So first, a fixed mass proportion. This is the law of definite proportion. Let's say I have a 100-gram sample of sodium chloride. If I actually separated that out into the individual ions, I would find that I have 39.3 grams of sodium in here and 60.7 grams of chlorine. Now, technically speaking, in this case, it becomes chloride when it makes the sodium chloride. But if I separated them out into their individual species before they were reacted, I would have 39.3 grams of that be sodium, 60.7 grams of that be chloride, the chlorine coming in. If I actually looked at the difference here, the mass of chlorine versus the mass of sodium, the ratio here is 1.54. What that means is there's basically 1.5 times the mass of chlorine to every sodium that I have. If I examine a 200-gram sample of sodium chloride, I see that I have 78.6 grams of sodium and 121.4 grams of chlorine. I look at the ratio and it's the same ratio. So I have a 58.44 gram sample of sodium chloride. It contains 22.99 grams of sodium and 35.44 grams of chlorine. Same ratio again. And this number is important. This number we're going to see in a little bit is called our molar mass of sodium chloride. And so it's actually how we can convert between grams and moles, which we'll do so later on in this chapter. But the law of definite proportion showed us very intentionally that the substance has the same chemical makeup regardless of how it was made. So it doesn't matter what ratio I made it in, it's always going to have one sodium to one chloride. And in the mass ratio of 1.54, because a chlorine atom is just heavier than a chloride or than a sodium ion or sodium atom. And the law of multiple proportions. So this shows us, we're going to look at CO and CO2 specifically. So carbon can combine with oxygen to form two different substances, CO2, which is carbon dioxide, which as humans we breathe out, or CO, carbon monoxide, which is very, very poisonous to us because our bodies actually absorb it better than they do than they do O2. Carbon monoxide contains 1.3 grams of oxygen for every 1 gram of carbon. CO2 contains 2.67 grams of oxygen for every 1 gram of carbon. And notice the ratio there. 2.67 grams of um, oxygen to 1 gram of carbon versus 1.33 grams of oxygen to 1 gram of carbon. The ratio there is a 2. So there's always a whole number relationship between the oxygen masses. This has to be significant. This is how Dalton developed the atomic theory to help explain this law of multiple portions. Elements can combine in different ratios, but they will do so in whole numbers. So, for example, NO2, nitrogen dioxide, is a compound. N2O4 is another compound. They're combining in whole number ratios. It's not like a half of a nitrogen is going to combine with an oxygen. Okay? They're going to combine in whole number ratios. CH4 is a compound. C3H8 is a compound. They're combining in whole number ratios. And that's the idea behind the law of multiple proportions is that they can combine in different ratios, but they will be whole number ratios of the elements themselves.